Hey, hey, it's Dr. J. 5.4 is almost done. We're going to do the applications today. So a few different types of applications, in particular 2 different types. The first type is called LCM, least common multiple. And the second application we're going to do is barcodes, also known as UPCs. Universal Product Code. Okay. Let's take these one at a time. We'll start with the LCM. So here's the idea behind the LCM. When you have a modulus, suppose you have, I don't know, mod 10. The modulus essentially tells you who is acting like 0. So if you have a modulus of 10, that means that every multiple of 10 acts like 0. So it would be like having a clock that only has 10 different times, and every 10 hours or every 10 days or whatever, however we're measuring, the example I'm going to give, we're going to do years. Every 10 years would act like nothing. Like everything starts all over again. So 10 acts like 0. So you say 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you don't write 10, you write 0 because we're in mod 10. Okay. If we were in mod 4, much smaller modulus, it would look like this. Mod 4 would be like, the seasons, You have a summer, fall, winter, spring, summer, fall, winter, spring. And it just keeps going around those 4 seasons over and over and over and over again. And every 4 seasons, you're right back where you started, right? So if it's summer, what will it be in 4 seasons? Well, it'll be summer again, right? So and we're assuming we're going to go around clockwise in all of these. I don't think we're going to have any negative numbers, at least not in this particular example. So we can create a modulus called the Lcm modulus, which would be the least common multiple of the 2 moduli. So you have modulo 4, modulo 10. What would be the least common multiple? All right. So we call that the LCM of 4 and 10. Now, why would you want to do this? Well, you could think of these 2 moduli like clocks. That's the classic way to think about them. And so the LCM would tell you how often these 2 clocks would agree with each other. All right. In other words, when would they both be at 0? And then as soon as they start, they will agree for a minute, and then they'll lose it again. By the time this clock gets to 5, this clock will be back to 1 again, and then they'll be offset again, and then eventually they'll catch back up with each other. So if you think of them as clocks, the LCM tells us how often do these, and I'm going to use the word clocks, they don't necessarily have to be clocks, line up with each other. In other words, how often do they both point to 0? Okay. You're going to see that if you press go, these clocks would start ticking, and immediately the clocks would be off once you got past 3. Yeah, because once you get past 3, the modulo 4 clock would be pointing to 0, but the mod 10 clock would be pointing to 4. You see? So let's go ahead and do a calculation of the least common multiple. So how to find the least common multiple. There are actually two methods. One method doesn't have a technique. It's called the intuitive method. If you have a good understanding of the way numbers work, you just say, what is the smallest number that is a multiple of both 4 and 10? You don't have to do any math. You can just think about your life and your experience with numbers, and you would immediately know that it's 20. 20 is the smallest number that's divisible by both 4 and 10. Now, the intuitive method works pretty good for small numbers, and it works pretty good for students that have a very good understanding of how numbers work. They read the question, they know the answer, they don't have to do much math. Okay. I'm not going to be using method 1 very often, only if the numbers are very small. Method number 2 is mechanical. It's like making a little machine that would tell you what the answer is. So here we go, method number 2, the mechanical method. How do we do this? Well, we write down the two numbers. Let's say 10 and 4. It doesn't matter which one's on top and which one's on bottom. And you're going to factor them out into prime numbers. Factor these out into prime numbers. All right, so factor these into primes. Okay? And then form the LCM by taking the largest number of any given factor. The largest number, not the smallest. So sometimes we read it and it says least, and you think, oh, what's the least number? But it's a little bit counterintuitive. It's the least common. So number 4 has 2 2s. The number 10 has 1 2. And so the least common is 2 2s. Now, you have to include all of the prime factors that are in the given numbers. So this one is 2 and 5. You already have a 2, so you don't need to add a third 2. And then you're going to add 1 5. So the LCM is 4 times 5, which is 20. The same answer that I got intuitively. So if you were thinking of these clocks as going by the hour, then that would mean every 20 hours, it depends how you're measuring the clock. Not all clocks spin at the same speed when we're talking about modulus. If you're thinking about hours, that would be every 20 hours these clocks would line up with each other. If these were daily clocks, so the clock ticks once per day, it changes to the next day. These are really simple clocks. They only have one hand. Right? Then that would mean every 20 days these clocks line up. Let's do an actual real-world example. Once every 10 years, the United States, U.S., conducts United States government conducts a census of the population. In other words, counting the number of people that live in the United States. All right. Once every 4 years, the United States holds a presidential election. How often do both of these, and I'm assuming both of these meaning the census and the election, occur in the same year? Now, I kind of gave this one away with the warm-up. I already used these numbers intentionally, so I don't know why I'm calling this example 2. It's actually example 1. I think my brain was thinking we were already on our second example, but this is the first example. I'm just going to use the same numbers from the warm-up. So we have once every 10 years, once every 4 years. So we have the LCM of 10 and 4, which we already know is 20. So every 20 years. Yeah. Once every 20 years. In fact, this is one of those years. In the year 2020, we're having both the presidential election and a census. The next time that happens will be 2040. The last time it happened before this year was 2000. So every 20 years, the election, the presidential election, and the census will occur in the same year. Okay. Let's go to example 2 now. Let's talk about LCM of 3 numbers. Suppose we had 3 clocks all spinning, or 3 things all happening. When will all 3 of these line up? So let's say, what's the LCM of 10, 12, and 8? Line them up. You could try it intuitively. Can you just look at all of these numbers and go bam and just see what it is? If you have that intuitive sense, you have a gift. Okay? I recommend doing that or thinking that, writing that down, but you should still do the process to make sure that you're not just, cursed. The difference between a gift and a curse is about that much. All right, so again, we have 10, which is 2 times 5. We have 12, which is 2 times 2 times 3. And we have 8, which is 2 times 2 times 2. So the LCM, you want to take the largest number of factors that occur in any given number. So you're going to need 3 2s, 1 3, and 1 5. Okay, so that'll be 2 times 2 times 2 times 3 times 5. So the LCM would be, I don't know, you can do this on a calculator if you want. This is 8, that's 15, 120. Want to try another one? The LCM of 9, 14, and 28. Nine, 14, and 28. I think I meant to say 27, but I'm going to go with 28 since it's already out there. So we got 9 is 3 times 3. 14 is 2 times 7. 28 is 2 times 2 times 7. So the LCM, I usually go in order, so we need 2 2s. We do not need 3 2s because nobody has 3 2s. All right. We need 2 3s. And we need 1 7. It doesn't matter which 7 you use. Don't use them both because nobody has 2 7s, right? So it's the least common. I focus on the word common and I don't focus too much on the word least. What your answer ends up being the least, but when you're calculating it, I don't like to let the word least kind of throw you off. So it's 2 times 2 times 3 times 3 times 7. That's 4 times 9 times 7. 36 times 7. So this one is 252. Okay. Let's try an example. Suppose I water the yard once every 3 days. I have a desert yard, so I only have to do it once every 3 days. I get a car wash once every 6 days. And I go shopping once every 15 days. Yeah, I know it's about 2 weeks, but I go 2 weeks plus a day. That's every 15 days. How often do I do all 3 of these things? All of these chores on the same day. So we want the LCM of 3, 6, and 15. Again, you might see it, right? You got a gift, you're intuitive, then you can just read the question, write down the answer. It's 30, okay? If you have that intuition, it's 30. These numbers are pretty small, you can probably figure it out. But if not, you just do the math. So you got 3. 3 is already prime. So if something is already prime, you don't have to do it. All right. 6. 6 is 2 times 3. And 15. 15 is 3 times 5. So look, everybody has 1 3. So you're only going to need 1 3. You're going to need at least 1 2. And you're going to need a 5. You do not need all 3 of these 3s. You only need 1 of them. So once you've got 1 3, this 3 will account for the other 2 3s as well. They have that in common. And so there you go, 2 times 3 times 5, which is 6 times 5, which is 30. So once every 30 days. So basically once a month. I water the yard, I get a car wash, and I go shopping all on the same day. If I'm following this modulus, or these 3 moduli. Alrighty. The next thing we're going to talk about is barcodes, also known as UPC codes. Universal Product Code. It's funny, if you say UPC code, you're actually saying the word code twice because the C stands for code. So I know people say it all the time, UPC code. Well, you should really just say UP code because the word code, but nobody's going to get you for that. All right, those are these things. Yeah. Barcodes, product codes, beep, beep, beep. You go to the grocery store and you get something scanned. All right. I'm probably going to have to zoom in on this a little bit to get you to be able to see that. So let me just put this aside. UPC codes are a 12-digit number. And I'll just write one out kind of big here. Let's see. 8. There's usually a space, 45001. 00072, and then 9. So it's a 12-digit number, something like this. And it's usually right underneath the bars, so you'll see the, the bars will be above it like this, and this is what it would look like. Kind of like one of these guys. So the digits actually mean something. The first digit tells you the type of code. There are basically 10 different types of codes. So this can be anywhere from 0 through 9. So there are 10 different types of codes. And they're used for different types of products. The next group tells you who made the product. So this is the manufacturer. Yeah, so who made it. So if you go buy, try this, go buy 5 products all from the same company, and you'll notice that these 5 digits are all the same. Yeah. The next 5 identifies the product type. Okay. It's kind of like the type of code, except for the type of code is a more general category. So let me give you an example. The type of code could be 8. This could mean boxed foods or something. But then this would tell you it's macaroni and cheese. Yeah. There's another one. I think if it's a 9, it's a book or something. Yeah. So you know it's a book. But then this will tell you exactly which book it is. So these 2 codes kind of go together. This tells you what type of code it is, and then this tells you the type of product. Yeah. Is it, mac and cheese? What is it? Now, the most important digit is the last digit. This last digit is called the check digit. This digit verifies that the code is correct. That way, what it does is it makes sure that there is no mistake anywhere else in the code. If one of these numbers gets omitted, or if somebody messes with it and tries to alter the code in any way, this digit will check whether or not it's correct or not. And this is the way it works. we list out the digits in the following way. A1, A2, A3, A4, A5, A6, A7, A8, A9, A10, A11, A12. So there should be 12 different A's. Right? Each digit is called A. Then we evaluate 3A1 plus A2 plus 3A3 plus A4 plus 3A5 plus A6. So every other A is going to get a 3. All right, it's easy to remember. It's the odd ones, all the ones that have an odd index. So 3A7, and then A8, and then 3A9, and then A10, and then 3A11, and then A12. Okay. If this is a valid code, then this sum should be equal to, let's call this sum A, will be equal to or be congruent to 0 modulo 10. In other words, A is equal to 0 mod 10. So this is how the check digit works. That digit better be the right digit. Otherwise, it's the last digit. That's A12. A12 is called the check digit. In this example, I could call it X or something like that in a little bit. All right, so that's how the code works. You want to see it? Let's see if this is a valid code. I just made this code up. I don't know if it's valid or not. I mean, I took it from a real product, but I made up the numbers. Okay, so let's see. Is this code valid? Let's do it. So we got 3 times 8 plus 4 plus 3 times 5 plus 0 plus 3 times 0 plus 1 plus 3 times 0 plus 0 plus another 3 times 0. I tried to skip the zeros when I did this on my own, and I kept screwing it up. So put the zeros in, and then you can omit them after you've written them all down. If you try to skip them, you'll get off count. It happened to me several times, and I thought, what am I doing wrong? And then plus 7 plus 3 times 2 plus 9. I know I'm getting kind of squirrely over there. Let's try it over here. 24 plus 4 plus 15 plus nothing. You can skip it. Plus nothing, skip it. Plus 1 plus nothing, nothing, nothing. Plus 7 plus 6 plus, and there's that 9 you can barely see. I'll bring it over there so you can see it. That's a 9. All right. This should be equal or congruent to 0 mod 10. Remember what 0 mod 10 is? It's just a multiple of 10. So as long as this comes out to be a multiple of 10, then it's valid. Why don't I use a calculator since we've got one? If you want to do this all by hand, certainly can. I've got a calculator here, so let's go ahead and do it. We've got 24 plus 4 plus 15 plus 1 plus 7 plus 6 plus 9. It's equal to 66. Is that congruent to 0 mod 10? No. So this code is not valid. 66 is not congruent to 0. 60 would be, 70 would be, 80 would be. Any multiple of 10 would be valid. Okay. Want to try another one? Determine if the UPC code is valid. And again, you don't really have to say the word code. I just did, but it's UPC whether it's valid or not. I've got one blown up here for you. Okay, so I got 0, 3, 6, 0, 0, 0, 2, 9, 1, 4, 5, and then the check digit is 2. This is my UPC code. I'm just copying all of these digits on the bottom here. Okay, so let's see. We got 3 times 0 plus 3. Plus 3 times 6 plus 0 plus 3 times 0 plus 0 plus 3 times 2 plus 9. Oh man, I'm running out of room. Plus 3 times 1 plus 4. So every other term gets the 3. 3 times 5, and then plus 2. I ran out of room for these last ones, so I put them down here. 3, 4, 5, and 2. All right, so I got 3 times 0. That's 0 plus 3 plus 18 plus 0, 0, 0 plus 6 plus 9 plus 3 plus 4 plus 15 plus 2. I don't need that first 0 either. Strike that out. So I've got a 3 plus 18 plus 6 plus 9 plus 3 plus 4 plus 15 plus 2. 60. Yep. Is 60 congruent to 0 mod 10? Yes. 60 is congruent to 0 mod 10. 60 is a multiple of 10. So this is a valid UPC code. It means that this came from an actual product in the store. I don't remember what it was. Again, the 0 here tells you what type of product. The 36,000 is the company, manufacturer. Here's the product code, the 29145. So whatever that is. And then the 2 really means nothing. Well, it means that the check digit was checked out. It checks out. All right. Next, we're going to do some examples of finding a missing digit. Find a digit that's missing. So we're going to solve for x. So we'll do several examples. The last one is the one that we're actually going to need for the barcode problem again. These other two are just to kind of get the idea going. So the way you solve a modular equation is exactly the same way you solve an ordinary algebra equation, but you got to keep the modulus in mind. So we're going to go x plus 8. So x minus 8 plus 8, those will cancel out. 3 plus 8 is 11. Yeah. But what is 11 congruent to mod 4? So x is equal to 11, but it's not congruent to 11. It's equal to 11. Mod 4, what does 11 mean? 11 actually means 3. Yeah. It's 3 more than 8, and 8 is a multiple of 4. So x is equal to 3. For these, you can actually just use the old-fashioned equal sign as opposed to the congruent sign. You don't have a congruent symbol on your computer, so you could just use the normal equal sign. All right, same thing here. We're going to subtract 15. Uh-oh, we're going to get a negative number. Yeah, so x is going to be equal to negative 13. But what is that mod 7? Well, divide. What's 13 divided by 7? That's 1. Yeah, 13 divided by 7 is 1. What's the remainder? I think I can hear you. 6? Yeah, but because it's negative, it'll be negative 6. So what is negative 6 congruent to? 1. Yeah. You think about it. If you're mod 7, that's like a clock, for the days of the week, you only have 7 possibilities. Remember, 7 is the same as 0. And if you're going negative, you go around counterclockwise. So this would be negative 1. This would be negative 2. Right? Negative 3. Negative 4. Negative 5. Negative 6. Yeah, we're trying to get to negative 13. So negative 7. Negative 8. Negative 9. Negative 10. Negative 11. Negative 12. Negative 13. There it is. So it is congruent to 1. So you can just say x equals 1. I'm putting my answers over here. These are mostly just for fun and play and algebraic, experience. I'm not actually going to use these problems in the example. In the application example, I'm going to use this one right here, the one that's congruent to 0. This is the one that's actually useful. So we've got x plus 62. We're going to subtract 62 from both sides. Yeah. So that means x is congruent to negative 62, or is equal to negative 62 mod 10. We often frequently go back and forth between congruence and equality. When you're talking about mods, they mean the same thing, so we're not going to make a big deal about whether I use 3 bars or 2 bars. In reality, when you're doing this, you can just use 2 bars on your paper. Nobody's going to know, as long as you know that it's congruent. All right, what is negative 62 mod 10? Negative 62 mod 10. So we got negative 62 divided by 10. Yeah. That's going to be negative 6, remainder negative 2. In other words, it's negative 6 times 10 plus negative 2. Yeah, this is another way of thinking about what does negative 62 actually mean? It means negative 6 times 10, because that's the modulus, plus negative 2. So x is really just equal to negative 2 mod 10. All right, make your mod 10 clock. And go backwards 2 units. Starting right here, you're going to go backwards 2 units. So negative 2. Negative 2 is the same as 8. So in this example, x would be equal to 8. So here are your 3 answers. X is equal to 3, x is equal to 1, and x is equal to 8. Or you could also say congruent to that value. Because it's not the actual value that we get, it's the congruent value. All right, well, the last thing we're going to do is find the missing digit for the UPC code. Just making sure I got the right numbers. So here we go. This is the last example. Find the check digit in the UPC that makes the UPC code, the UPC valid. So it must be valid. So the check digit is called X here. And this is the way the digit is typically written. The first digit and the last digit are usually a little bit higher than the other digits. Although they're not always written like that. Sometimes they're all written equally. But this is like the traditional bar code. You got your bars like this. I only have one copy of the big one, and we already did that one. So this is my made-up one. All right. So what must X be in order for this code to be valid? Let's do it. All right. We got 2 times 3, first digit times 3, plus 1, 0 times 3, plus 0, 3 times 3, plus 5. 4 times 3 plus 2, 0 times 3 plus 1, plus 6 times 3, and then plus x. You can't see that, plus x. So I've got 6 plus 1. The dogs are barking at the mailman. Plus 5, plus 12, plus 2. Cross off all the zeros, don't matter. Plus 1, plus 18, plus x. All right. And I want that to be congruent to 0 mod 10. Might as well use our calculator since I brought it out. So we've got 6 plus 1 plus 9. Probably could have done this while I was grabbing the calculator. You might already have the answer. Plus 12, plus 2, plus 1, plus 18. So all of this, if I did it correctly, should come out to be 54. All right. So now you're going to solve this equation for x. So I've got 54 plus x is congruent to 0 mod 10. You probably can guess what it's going to be, right? 6. Yeah. You can even just do mental math. 54 plus 6 would be 60. And that's a multiple of 10. But in case you don't get the mental math, I'll show the steps. So we're subtracting 54. We get negative 54 mod 10. Yeah. Negative 54 is equal to negative 5 times 10 plus negative 4. Yeah. Or you could do negative 54 divided by 10. It's the same thing. 10 goes into 54 5 times with a remainder of negative 4. Remember, because this is a negative, it has a negative remainder. So this is congruent to negative 4 mod 10. I've never seen a negative number on a barcode, and you never will. The smallest number on a barcode is 0. So mod 10, remember you're going around counterclockwise. Negative 4 means to start at 0 and go negative 4. 1, 2, 3, 4. So this is negative 4. The answer is x is equal to 6. Or technically it's congruent to 6 mod 10. But you can just say x is equal to 6 because it's a digit. That's the digit that'll actually be on the barcode. You won't see this on a barcode. You'll see this, the actual number 6. Okay, we are done with Chapter 5. We also finished Chapter 4, although it was cut short because of the virus. So we have a short Chapter 4 and a complete Chapter 5, and that'll be the test tomorrow, Thursday. Have a good one. Do your homework. The test is open notes, so bye-bye.